In a standard 200 amp service, if a satellite dish takes a direct lightning strike, it would likely ground properly assuming certain conditions are met. Firstly, the lightning grounding system must be properly installed and maintained. Secondly, the bonding system must be intact, providing a low resistance path to ground. Thirdly, the lightning ground rod should be properly sized and installed to handle the surge. The lightning grounding system is designed to provide a low resistance path for lightning to discharge into the ground, minimizing the potential for damage to the building or its occupants. The bonding system connects all metal components and service entrances to the lightning ground rod, ensuring they are all at the same electrical potential and preventing current from flowing through other paths. The lightning ground rod provides a direct connection to the earth and dissipates the lightning energy into the ground. It's generally not necessary to ground the satellite dish to its own rod if the aforementioned conditions are met, because the bonding system will provide a sufficient path to ground for the dish, and installing a separate ground rod would be redundant. However, if there is any evidence of structural damage to the satellite dish or its mounting system, it is recommended to have it inspected and grounded to a separate rod for added protection. Bonding is crucial for electrical safety. It involves connecting all metallic parts of a system to create a low impedance path for fault currents. This helps to ensure that in the event of a fault, such as a lightning strike, the current will flow safely to ground without causing dangerous voltage differences. The main purpose of bonding is to minimize the risk of electric shock and fire. Grounding, on the other hand, is the connection of the electrical system to the earth. The ground rod, typically made of copper or copper-clad steel, is driven into the earth to provide a direct path for fault currents to dissipate. The grounding system helps to stabilize voltage to prevent electrical hazards and protect equipment from damage due to overvoltage. A properly installed grounding system is essential for lightning protection. Without it, the lightning strike energy could find other paths to ground, potentially damaging electrical appliances or even causing a fire. The National Electrical Code, or NEC, provides guidelines for proper grounding and bonding practices. It outlines the requirements for the size and type of grounding conductors, the installation of ground rods, and the bonding of metallic components. It is important to follow the NEC guidelines to ensure the safety and effectiveness of the electrical system. When evaluating a grounding system, several factors should be considered. These include the soil resistivity, the size and type of grounding conductors, the bonding connections, and the presence of any structural damage. Soil resistivity affects the effectiveness of the ground rod. Low soil resistivity allows for better dissipation of fault currents. The size and type of grounding conductors should be appropriate for the size of the electrical system and the potential fault current. Bonding connections should be tight and corrosion resistant to ensure a reliable path to ground. Any structural damage to the satellite dish or its mounting system could compromise the grounding path and should be addressed immediately. If there is concern about the effectiveness of the grounding system, it is best to consult with a qualified electrician. They can perform a ground resistance test to verify the integrity of the grounding system and recommend any necessary repairs or upgrades. Lightning protection systems typically consist of air terminals, also known as lightning rods, conductors, and grounding electrodes. Air terminals are installed on the highest points of a structure to intercept lightning strikes. Conductors are used to carry the lightning current from the air terminals to the grounding electrodes. Grounding electrodes, such as ground rods, provide a path for the lightning current to dissipate into the earth. Surge protection devices, also known as SPD, are designed to protect electrical equipment from voltage spikes caused by lightning strikes or other electrical disturbances. SPD are installed at the service entrance and at various points throughout the electrical system to divert surge currents to ground. The effectiveness of a lightning protection system depends on several factors, including the design of the system, the quality of the components, and the installation practices. It is important to have a lightning protection system designed and installed by a qualified professional to ensure its effectiveness. When installing a satellite dish, it is important to consider the potential for lightning strikes. The dish should be mounted in a location that minimizes its exposure to lightning. The dish should be properly grounded and bonded to the electrical system. Surge protection devices should be installed to protect the satellite receiver and other electronic equipment. In addition to grounding, bonding, and surge protection, there are other measures that can be taken to protect a building from lightning strikes. These include installing lightning rods, using non-combustible materials, and avoiding the use of metal objects on the roof. Lightning rods provide a preferential path for lightning to strike, directing the current safely to ground. Non-combustible materials can help to prevent fires caused by lightning strikes. Metal objects on the roof, such as antennas or satellite dishes, can attract lightning and should be properly grounded. The National Fire Protection Association, or NFPA, provides standards for lightning protection systems. NFPA 780 covers the installation of lightning protection systems, while NFPA 70, the National Electrical Code, covers grounding and bonding requirements. It is important to follow these standards to ensure the safety and effectiveness of lightning protection systems. Regular inspections and maintenance are essential for ensuring the continued effectiveness of a grounding system. Ground rods should be inspected for corrosion and damage. Bonding connections should be checked for tightness and corrosion. Surge protection devices should be tested periodically to verify their functionality. Any deficiencies should be addressed promptly to maintain the integrity of the grounding system. In summary, grounding and bonding are crucial for electrical safety, especially in areas prone to lightning strikes. A properly installed and maintained grounding system helps to protect buildings and occupants from electrical hazards and damage caused by overvoltage. Following the NEC guidelines and consulting with a qualified electrician can help to ensure the safety and effectiveness of the electrical system. If a satellite dish is properly bonded to the existing grounding system, a separate ground rod is generally not required. However, if there are concerns about the integrity of the grounding system or structural damage to the dish, a separate ground rod may be recommended. It's important to remember that electrical codes and best practices can vary depending on the local jurisdiction, so consulting with a qualified electrician is always recommended. Furthermore, surge protection devices at the service panel and sensitive electronic equipment can provide an additional layer of protection against lightning strikes. These devices help to divert excess voltage to ground, preventing damage to appliances and equipment. Grounding and bonding are not only important for lightning protection, but also for preventing electrical shocks. In a properly grounded system, if a fault occurs, such as a wire coming into contact with a metal enclosure, the fault current will flow back to the source, tripping the circuit breaker or fuse. This helps to quickly disconnect the circuit and prevent electric shock. Without proper grounding, the metal enclosure could become energized, posing a serious shock hazard. The size of the grounding conductor is also important. The grounding conductor must be sized appropriately to carry the maximum fault current. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the service entrance conductors. Using an undersized grounding conductor can create a high impedance path to ground, which can limit the effectiveness of the grounding system. In addition to grounding conductors, grounding electrodes are also essential components of a grounding system. Grounding electrodes provide a direct connection to the earth, allowing fault currents to dissipate. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The number and type of grounding electrodes required depend on the size of the electrical system and the soil conditions. Soil resistivity plays a significant role in the effectiveness of grounding electrodes. Soil with high resistivity, such as sandy or rocky soil, will have a higher resistance to ground. This means that it will be more difficult for fault currents to dissipate into the earth. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or use special soil treatment methods to reduce the resistance to ground. The location of grounding electrodes is also important. Grounding electrodes should be installed as close as possible to the service entrance and should be located in an area where the soil is consistently moist. This will help to ensure a low resistance path to ground. The installation of grounding electrodes should comply with the requirements of the NEC. The NEC specifies the minimum depth and spacing for grounding electrodes. It also requires that grounding electrodes be protected from physical damage. Bonding is another critical aspect of electrical safety. Bonding involves connecting all metallic parts of an electrical system together to create a low impedance path for fault current. This includes metal conduits, metal enclosures, metal water pipes, and metal gas pipes. The purpose of bonding is to ensure that all metallic parts are at the same electrical potential. This helps to prevent voltage differences that could cause electric shock. Bonding jumpers are used to connect metallic parts together. Bonding jumpers should be sized appropriately to carry the maximum fault current. The NEC provides tables that specify the minimum size of bonding jumpers based on the size of the circuit conductors. The installation of bonding jumpers should comply with the requirements of the NEC. The NEC requires that bonding jumpers be securely fastened and protected from physical damage. In addition to bonding metallic parts, it is also important to bond the neutral conductor to the grounding electrode at the service entrance. This is known as the main bonding jumper. The main bonding jumper provides a path for fault currents to flow back to the source and trip the circuit breaker or fuse. The size of the main bonding jumper should be based on the size of the service entrance conductors. The installation of the main bonding jumper should comply with the requirements of the NEC. Regular inspections and maintenance are essential for ensuring the continued effectiveness of a grounding and bonding system. Grounding electrodes should be inspected for corrosion and damage. Bonding connections should be checked for tightness and corrosion. Surge protection devices should be tested periodically to verify their functionality. Any deficiencies should be addressed promptly to maintain the integrity of the grounding and bonding system. It is also important to keep the area around grounding electrodes clear of vegetation and debris. Vegetation and debris can interfere with the effectiveness of the grounding electrodes. In summary, grounding and bonding are essential for electrical safety. A properly installed and maintained grounding and bonding system helps to protect buildings and occupants from electrical hazards and damage caused by overvoltage. Following the NEC guidelines and consulting with a qualified electrician can help to ensure the safety and effectiveness of the electrical system. Remember that electrical work can be dangerous and should only be performed by qualified professionals. Always turn off the power before working on electrical equipment. If you are not comfortable working on electrical equipment, call a qualified electrician. They will have the knowledge and experience to safely and effectively perform the work. The principles of grounding and bonding apply not only to residential electrical systems but also to commercial and industrial electrical systems. Commercial and industrial electrical systems often have more complex grounding and bonding requirements due to the larger size of the electrical system and the presence of sensitive electronic equipment. In commercial and industrial electrical systems, it is common to use a separate grounding conductor for sensitive electronic equipment. This is known as an isolated ground. An isolated ground provides a dedicated path to ground for electronic equipment, minimizing the risk of electrical noise and interference. The isolated ground conductor should be run directly from the electronic equipment to the grounding electrode, without being connected to any other metallic parts. Surge protection devices are also commonly used in commercial and industrial electrical systems. Surge protection devices can protect sensitive electronic equipment from voltage spikes caused by lightning strikes or other electrical disturbances. Surge protection devices should be installed at the service entrance and at various points throughout the electrical system to provide comprehensive protection. In addition to grounding, bonding, and surge protection, it is also important to use shielded cables in commercial and industrial electrical systems. Shielded cables help to reduce electrical noise and interference, which can disrupt the operation of electronic equipment. The shield of the cable should be properly grounded to provide a low impedance path to ground. Regular inspections and maintenance are even more important in commercial and industrial electrical systems due to the larger size and complexity of the electrical system. Grounding electrodes should be inspected for corrosion and damage. Bonding connections should be checked for tightness and corrosion. Surge protection devices should be tested periodically to verify their functionality. Shielded cables should be inspected for damage and proper grounding. Any deficiencies should be addressed promptly to maintain the integrity of the grounding and bonding system. It is also important to keep accurate records of all grounding and bonding system components and maintenance activities. These records can be helpful for troubleshooting problems and for ensuring that the grounding and bonding system is properly maintained. In summary, grounding and bonding are essential for electrical safety in all types of electrical systems, including residential, commercial, and industrial systems. A properly installed and maintained grounding and bonding system helps to protect buildings and occupants from electrical hazards and damage caused by overvoltage. Following the NEC guidelines and consulting with a qualified electrician can help to ensure the safety and effectiveness of the electrical system. Remember that electrical work can be dangerous and should only be performed by qualified professionals. Always turn off the power before working on electrical equipment. If you are not comfortable working on electrical equipment, call a qualified electrician. They will have the knowledge and experience to safely and effectively perform the work.